What's up, guys? Welcome to this video lecture in general topology. In this video, I'm going to discuss indexed sets, associated set functions, and algebra of real valued functions. Okay, so let's start with indexed sets and Cartesian products. Usually, if we have a class of sets or a collection of sets, and if we can count the members or elements of the sets, then we can just actually index the elements using the set of natural numbers. So for example, if we have, let me just write that. If we have this collection of, say, a sub I, where I is any natural number, then this class has an infinite elements, and we can write them a sub 1, a sub 2, a sub 3, etc., etc. Okay. However, we can count the elements, so this is a countable class of sets. Now, there are cases where the indexed set or the index set is not a countable set, or it is a subset of the set of natural numbers. So we simply denote the index set by I. So in that case, our collection of, or our class of sets is also not countable. So we name them an indexed class of sets. And the one that I have just written here is just a particular example of an indexed set. So we denote an indexed class of sets by the set of all a sub I, where I is an element of the set I, or simply we denote that by the set of all a sub I, where I is in capital I, or simply we can just drop the subscript I in capital I. So we simply write an indexed class of sets as the set of all a sub I. Okay, so an indexed class of sets assigns a set AI to each I, to each small I in the set capital I. Okay, so the set I is called the index set. The sets AI are called indexed sets, and each I in capital I is called an index. So when the index set I, or capital I, is the set of positive integers, then the indexed class A1, A2, etc. is called a sequence of sets. For example, for each small n in the set of natural numbers or the positive integers, we let d sub small n be the set of all x, such that x is in the set of natural numbers and x is a multiple of n. So in that case, d1 is just the set of natural numbers, d2 is the set of positive integers, d3 is the set of all positive multiples of 3, etc., etc. Okay, so let us now proceed to the Cartesian product of indexed class of sets. Okay, so we use capital Pi to denote Cartesian product, especially when we're going to perform multiplication of several sets. So if we have a family of indexed class of sets, so we denote it by script A, so it's the set of all AI, where I is in capital I. Then the Cartesian product of every element a sub I in script A is denoted by pi of every AI where I is in capital I, or simply pi of a sub I for all I. Okay, so the Cartesian product is the set of all functions small p from the index set I to the union of all a sub I such that p of I is equal to small a sub I, which is an element of capital A sub I. So we denote such an element of the Cartesian product by P, which is the collection of AI for I in capital I. Okay. So for each I sub O in capital I, there exists a function pi sub I sub O called the I sub O projection function, or the I sub 0 projection function from the product set pi of A sub I into the I sub 0th coordinate set given by pi sub I sub 0 of AI for I in capital I is equal to A sub I sub 0. Okay, for example, recall that R cube is just the cross product of three R's. So that's R cross R cross R. So it consists of all three tuples denoted by P with entries A1 or arguments A1, A2, and A3 of real numbers. Now, we let R1, R2, and R3 denote copies of R. Then P can be viewed as a function on I, which consists of the numbers 1, 2, and 3, where P of 1 is equal to A1 in R1, P of 2 is equal to A sub 2 in R2, and P of 3 is equal to A sub 3 in R3. In other words, R cube is the product of R sub I in I, where R sub I is equal to the set of real numbers. Okay, so example 27 here illustrates the definition given in definition 21. Okay, so let us now proceed to the generalized set operations. So if you can recall, we discussed set union and set intersection. So let us now go back to those two operations, but this time we will be dealing with indexed class of sets. Okay, so the definitions are the same. For the union, we write the union of an index class of sets as the union of all set A, where capital A is an element of script A. So it's the set of all elements X, where X is in the universal set, and such that there exists a set A in the index class of set script A, such that we can find small x in that set, capital A. For the intersection, we have the intersection of all A for all capital A in script A is the set of all x in the universal set U, such that x is found in A for every set A in the script set, in the set script A. Okay? So let us illustrate. Suppose our index set is the unit interval from 0 to 1. And then for every number on this interval, so we denote that by I, we define A sub I to be the interval from 0 to I. Okay, let's show that on the real line. So our I is the unit interval from 0 to 1. This is 0. This is 1. So that's our I. We define A sub I to be the set 0 to I. where small I is in capital I. So arbitrarily, if I is here, then this will be our A sub I. So we can actually move this number this number I from 0 to 1. So AI is a set or an interval that starts at 0 and ends on I, which is a number from 0 to 1. Okay, so if we're going to get the union of all A sub I, we can get the entire interval I, or the unit interval 0, 1. But if we're going to get the intersection of all A sub I, then take note that every set A sub I contains the element 0. So if we're going to get the intersection of all the A sub I's that we can define for the number I from 0 to 1, then the common element of all those sets will be the element 0. That is why the intersection of all A sub I is the singleton set containing 0. Another example, if D sub n is the set of all multiple of n, where n is any natural number, then the union of all D sub I for I greater than or equal to 10 will be the set of positive numbers from 10 to infinity. And their intersection will be empty. Okay? So walang common na elements yung mga D sub n natin. All D sub n. If we're going to consider all D sub n, then wala tayong makikitang common na element sa kanilang lahat. So they have an empty intersection. We can also generalize the distributive property. Okay, so we can distribute the union over the generalized intersection, and we can distribute the intersection over a generalized union. So it's given in Theorem 6. So in I, we get the union of B and the generalized intersection of AI, or the indexed intersection. So the intersection of AI. So by distributive property, that is just actually equal to the intersection of the indexed intersection of B union every A sub I. And for the second case, we have B intersect that to the generalized union or the indexed union A sub I. That will just be equal to the union for all I of B intersection A sub I. And then Theorem 7 gives us De Morgan's laws in terms of indexed sets. So we have script A is our indexed class of sets. So the entries or the elements are denoted by A sub small I. Then if we're going to get the complement of the generalized union or the union of all A sub I, then that is just equal to the intersection of the complement of every A sub I. And for the other way around, the complement of the indexed intersection is equal to the union of the complement of every A sub I in the class. Okay? So, pretty much the same lang talaga yung mga concepts na to. In-extend lang natin to an indexed class of set. So, walang bago sa mga concepts dito. Okay, so let us now proceed to section 2.3. We have a mapping F from X to Y, And we denote the image of the function f, or we denote the image of the set A under the mapping f, where capital A is any subset of the domain X of the function f, by f bracket of A. Okay, so that's our notation for the image of a subset capital A of the domain X of the function f. So it's f bracket of A. It's the set of images of points in A. So let's show that here. So we have a mapping f from X to Y. So let's say this is our X and this is Y. Okay, and then we have, say, elements A and B in X, which are contained in A. Thus A is just a subset of X. And suppose that A is mapped to, let's say W, and B is mapped to Y. Then from this diagram we have the image of A is equal to the set of images. So it is the image of small a, because small a is contained in capital A, and the image of small b. So this is the set containing W and Y. So yun lang yung f of A. Okay, yung inverse image naman ng any subset capital B ng counter domain Y, we denote that by f to the negative 1, or f inverse of capital B, is the set of points in X whose images lie in B. Okay, so using functional notation, f of A, or f of capital A, or f bracket of A, is equal to the set of all f of X where X is in capital A. Samantalang ang f inverse of capital B, or f inverse bracket of capital B, is the set of all X in capital X, such that yung image ni small x under f is found in B. So gawa tayo ng another mapping. So f from X to Y. This is our X and this is Y. This is the mapping F. I forgot to write here the mapping F. So suppose meron tayong A, B, C, D, E. So si A, nakamap siya kay say 1. Si B is also mapped to 1. C is mapped to 0. D is mapped to negative 1. And E is mapped to 2. And consider this set to be the set capital B. Okay, so we get here f inverse of capital B. By definition, this is the set of all X in capital X, such that the image of small x is found in B. So ano yung pwede nating i-collect na small x's or elements ni capital X na nakamap to an element which is found in B. So alam natin na si A, B, C, sila yung mga nakamap to 1 and 0, and 1 and 0 yung element ni capital B. So yung makukollect natin dito ng mga x's are A, B, and C. Yan. Yan yung definition ng inverse image. Okay, so we have an example here. Example 30, where f is a mapping from the set of real numbers going to the set of real numbers and is defined by f of x equals x squared plus 1. So, ibig sabihin nito, yung input x natin, yung kamap niya is yung square plus 1 nung number na yun. So, for example, if we are going to get the image of the set containing negative 1, 3, 4, and 7, para makuha natin yung mga images na yan, hindi isa-substitute lang natin itong apat na numbers na yan dun sa rule ng mapping natin, which is squaring plus 1. So, we get the square of negative 1 plus 1, kaya nakuha natin yung positive 2. Para naman sa number 3, square natin siya plus 1, we get 10, etc., etc. So, we simply square each of the elements of this set containing negative 1, 3, 4, and 7 and add 1 to their squares respectively. On the other hand, if we're going to get the inverse image of the interval from 2 to 5, so if you consider here the graph below, that's the function f of x equals x squared plus 1 is actually a parabola with vertex at 0, 1, and it opens upward. So if we look at the interval from 2 to 5 with respect to the y-axis, we can see that the inverse image, as shown by the pink lines, it's an interval in the set of on the horizontal axis, shown by the pink lines. So it's from the interval from negative 2 close and open to negative 1. Yun the interval from 1 to 2. So open in 1 and closed to 2. Okay, so why is that? Because our B here is the half open, half closed interval from 2 to 5. Okay. Okay. Let us now discuss some properties of associated set functions. So let's have Theorem 9. Here we have a mapping f. It's an arbitrary function f from x to y. And then we have subsets a and b of x. Okay, so Theorem 9 gives us some results on the direct image of unions and intersections and set difference. So in number 1, the direct or the image of the union of the sets A and B is just equal to the image of A union the image of B. Okay, but in number 2, the image of A intersection B is only a subset of the intersection of the image of A and the image of B. In number 3, we have the image of A minus B contained. So it is a larger set compared to the image of A minus the image of B. And lastly, in number 4, if A is a subset of B, then the image of A is also a subset of the image of B. Okay, so to show these 4 properties, for example, in number 1, we have equality of 2 sets. So we have to show that one set is a subset of the other, which means papakita natin that yung image ni A union B is a subset of the image of A union the image of B. And we also have to show that the image of A union the image of B is also a subset of the image of A union B. Okay. Sige, try natin yung Theorem 9 part I, f of A union B is equal to f of A union f of B. Sorry, dapat bracket to. Okay, so we start with an arbitrary element x in f A union B. Or this is equivalent to saying x is an element of, by definition, f of A union B is the set of all f of x such that x is in A union B. Or this is the set of all x such that f of x, or x is in A, or the set of all f of x is in B. So this means x is in f of A, or x is in f of B. Therefore, x is in f of A union B. Okay, so actually pwedeng baliktarin lang din natin ito. So we start here. Sige, start na. Mali. Union f of B. Okay, so pag dito naman tayo magsa-start, we let x be in f of A union f of B. Then this is equivalent to saying x is in as an element of the set of all f of x such that x is in A, or x is in, or the set of all f of x such that x is in B. Okay, so that will just be the same, the set of all f of x such that x is in A, or x is in B. Or x is an element of f of x such that x is in A union B, or x is in f of A union B. Therefore, f of A union B is just equal to f of A union f of B. Okay, so for the second case, you have to show that, you start with an element x, arbitrary element in the image of A intersection B, and you're going to show that that arbitrary element is found in f of A intersection f of B. Okay, so 2, 3, and 4 will be left as an exercise. Anyway, the second part is shown already. The proof of the second part is given in the instructional materials. Okay. And in example 31, we show here that the inclusions of part 2 and part 3 in Theorem 9 cannot in general be replaced by equality. So if you can see here, sa number 1 lang yung may equality. Okay. Okay. Yung Theorem 10 naman, yung binigay niya ng mga results is in terms of inverse images. So dito, mabilis lang to kasi sa inverse images, lahat equal yan. So for example, the inverse image of A union B is just equal to the inverse image of A union the inverse image of B. The inverse image of A intersection B is also equal to the inverse image of A intersection the inverse image of B. The inverse image of A minus B is equal to the inverse image of A minus the inverse image of B. And lastly, if A is a subset of B, then the inverse image of A is also a subset of the inverse image of B. Ayan. So, mabilis lang ma-memorize or matandaan itong mga results in terms of inverse image of a function. Okay, so we have a corollary, which is just a special case of the third part. Okay, we know that the inverse image of y is the codomain of the mapping F. So its inverse image should be equal to x. Okay, so as a special case of the third part, if A is any subset of y, then the inverse image of A complement is equal to the complement of the inverse image of A. Okay, so since this is just a corollary, it's a direct consequence of the third part. Corollary 1, yung proof niya will be left as an exercise. And then in Theorem 11, we have, again, we have a mapping F from x to y. A is a subset of x and B is a subset of y. Then, A will be a subset of the composition of F inverse and F, whereas B contains the composition of F and F inverse of evaluated at B. Okay? Okay, lastly, we have algebra of real valued functions. Okay, so before we discuss the properties, let's discuss some notations here. So we denote by script f of x comma r the collection of all real valued functions defined on some set x. So ibig sabihin itong script f natin, yung script f natin, collection yan siya ng lahat ng functions whose domain is the set capital X. Ayan, ganito na lang. Ano mga elements niya? F from X to pwedeng R, F from X to ang ganyan na lang. Okay. So it should be a mapping from X to R. So whatever the rule, as long as the domain is X and the codomain is the set of real numbers, then that function f will be an element of script f of x comma r. Okay. So we define this one. Okay. Define natin tong set na to of functions kasi gusto nating we want to operate on functions. So itong elements ni script f are called real valued functions. So this is the set of real valued functions. Okay, so since the images, we will be operating on f. Okay, so since the images are real numbers, we can operate on them. Okay, diba we have operations on involving the set, involving real numbers. Okay, so we define here the sum of two functions, of two real valued functions, then a function f multiplied by a real number k or a constant k. Then we have the absolute value of function f, the product of two functions f and g, and then the sum of a function f and an arbitrary real number k. So their definitions are given on the right side. So for example, f plus g is also a mapping from x to r and is defined by f plus g of x is simply the sum of f of x and g of x. So, and f times g is also a product from x to r and is defined by f times g of x is equal to f of x times g of x. So, ganun lang kasimple, class. So, for example, para sa absolute value, di kukunin lang din natin yung absolute value ng function evaluated at x. For the product k times f, we get k times f of x. And for the sum f plus k, we have f plus k of x is just equal to f of x plus k, since k is just a constant. So, meron tayong mga example dito. In example 32, illustrate natin some of the operations. So, f is a mapping, ayan, finite lang. Yung entries niya are A1 and B3. Ibig sabihin, A is mapped to 1, B is mapped to 3. So, si G dapat, yung domain niya is also the set containing A and B. So, dito sa G, si A is mapped to 2 while B is mapped to 1. Again, so X here is the set containing A and B. So, since F and G have the same domain X, and they are both real valued functions, then we can operate on them. So, for example, meron tayo dito, 3f minus 2g evaluated at a will just be 3 times f of a minus 2 times g of a. So, ganun lang kasimple, class. However, 3f minus 2g evaluated at b is equal to 11. We can also compute the absolute value of g of x. Okay, so ano yung g natin? 2 and 1 lang naman yung images. So, the absolute value of g plus 3. Oh, no. Not the absolute value. G plus 3 of x is g of x plus 3. The absolute value of g is a to b1. Yeah. Anyway, G is just, yung mga images niya positive naman. Kaya parang walang nagbago sa absolute value ni g. Let's have another example. Suppose we have G is a mapping from say A, B, C going to R given by G of A equals negative 3, G of B is equal to 1, and G of C is equal to negative 5. So, as a set of ordered pairs, G is the set containing A negative 3, B 1, and C negative 5. If we're going to get the absolute value of G, then we will have A3, we simply get the absolute value of negative 3, so it's positive 3. B1 because 1 is positive, and C positive 5. Okay. So, if you're familiar in elementary in your elementary mathematics na mga subjects, the set of real numbers is actually a field. Okay? It satisfies the field properties. Okay, so ano ba yung mga properties na yun? We have associativity, commutativity, existence of identity elements with respect to the operations addition and multiplication, etc., etc. Okay, ito namang set of all real valued functions denoted by script f of x comma r is real linear vector space. A vector space is isipin na lang natin, a vector space is a set that satisfies some properties. So for example, we have the operations of additions of functions. We have the associativity property, the commutativity property, and the existence of identity function. Yun yung mga properties na yun. And then existence of inverse function. Okay, so pretty much similar dun sa field property ni R. And then we have the operation of scalar multiplication. We have, okay, so 1 acts as an identity because when we multiply f by 1, we will just get f, and then if we multiply if we multiply k prime times f by another real number k, then that is just the same as we multiply f by the product of k and k prime. And then for the operations of addition and scalar multiplication, we have distributive property lang. So we can distribute a scalar. If we multiply a scalar to the sum of two functions, pwede natin siyang i-distribute. So yun yung sa number 1. Para naman sa number 2, if we have a sum of two scalars and then we multiply that to a function f, pwede lang natin i-distribute si f. I-multiply natin dun sa sum ng dalawang scalars. And lastly, we have the idea of a bounded function. Okay, so a function which is an element of a real valued function is said to be bounded if we can find a positive or a real number m such that the absolute value of f of x is always less than or equal to that number m for every x in the domain capital X. Okay, so we denote by beta of x of r the collection of all bounded functions in script f of x comma r. Okay, so an example of a bounded function is f of x equals sine of x. This is an example of bounded function kasi yung graph nito class is just a wave. Wait. The sine of x passes through 0. Yan. Or f of x is equal to the cosine of x. However, f of x equals x squared is not bounded. The graph of this is a parabola with vertex at the origin, and the graph extends indefinitely upward. So we cannot find a real number m that will contain f of x, the absolute value of f of x for any value of x. Okay, another example of a bounded function is f of x equals 1 over x squared plus 1. So this is bounded. If I'm not mistaken, the graph of that is something like this. If this is 1, yan. So that's a bounded function. So ano lang, you just have to know the graph of the function, and tingnan ninyo if it is bounded by some interval with respect to the to the vertical axis, because if it is not contained by some finite interval with respect to the vertical axis, then it is not a bounded function. For example, if we have a straight line, okay, we know that a straight line will go indefinitely on two directions. So kung nakaslant yan siya, ay hindi natin siya mako-contain at finite interval with respect to the vertical axis. Or if we consider this graph, this is an exponential function, that is not a bounded function. Okay, so that's all for this video. That's the we have actually discussed everything in chapter 2, so I'm going to give you an assignment. So I'm going to post these chapter exercises in MS Teams maybe later tonight, and then you can submit your answers there. Okay, so see you in the next video. Bye.